This problem asks us to find the area enclosed by a parametric curve and the y-axis. The parametric curve is defined as x being equal to t squared minus 2t and y being equal to the square root of t. The first thing we'd like to do is to get the t out of the middle of this equation. So we can notice that if we have y equal to the square root of t, then by squaring both sides of the equation, t must be equal to y squared. And we'll substitute that in to the equation for x, so that x is equal to y squared squared, which is y to the fourth, minus 2 times y squared. It'll be important for us to find the places where the curve intercepts the y-axis, since we're trying to find the area in between that curve and the y-axis. The intercepts occur when x is equal to 0. So we'll plug in 0 for x, set that equal to our y to the fourth minus 2y squared, and get to work finding the solutions. We'll factor out a y squared, leaving us with y squared minus 2, and then solve each factor on its own. Y squared is equal to 0 when y is 0. Y squared minus 2 is equal to 0 when y is equal to either negative square root of 2 or positive square root of 2. So we line up the three intercepts that we found, and we'll take integrals over the two intervals from negative root 2 to 0, and also from 0 to the positive square root of 2. And if either one of these is negative, we'll take the absolute value of it, since area has to be expressed as a positive number. In general, when we're trying to find the area between a curve and the y-axis, it's the integral of x times dy. We'll rewrite x in terms of y to make the antiderivative simpler. We'll focus on that first interval from negative square root of 2 to 0, and replace x with the expression that we had found for it earlier. The antiderivative is 1/5 y to the fifth minus 2/3 y cubed. We'll plug in 0 first and get 0 minus 0, and then plug in the negative square root of 2, which gives us negative 4 root 2 over 5, and then minus another negative of 4 root 2 over 3. From here, we'll take the two negatives and turn them into a positive, and by combining like terms and distributing that negative through our result, we get 12 root 2 over 15 minus 20 root 2 over 15, which is negative 8 root 2 over 15. We're halfway done. Now we need to take the integral of the other interval that we had found between 0 and positive square root of 2. Here the math turns out to be pretty much exactly the same as with the first integral. There are a couple different signs along the way, but in the end, the final result is exactly the same. 12 square root of 2 over 15 minus 20 root 2 over 15, which is negative 8 root 2 over 15. Area has to be expressed as a positive quantity, so we take the absolute value of each of these two pieces that we've calculated separately, leading us to a final enclosed area between the curve and the y-axis of 16 root 2 over 15.